Okay, so this is rather sad, right? You see this cyclohexane has lost 2 of its axial bonds here, but nevertheless we can still show you one more time what is the ring flip of cyclohexane. So here we go. Okay, let's use a ball, okay, a bit smaller. Oops, can't fit. Okay, wait. Here. Axial. Okay, ring flip. I'll be gentle this time. What do you notice? It become equatorial. So it means that, right, in the ring flip of cyclohexane, whichever that was initially axial, after the ring flip become equatorial, and vice versa. Okay. Now for the ring flip chair conformation of cyclohexane, there are actually some kind of an intermediate conformation. Okay, but this slide here, because you're not doing chemistry as a major, is only for your information. No need to know how to draw those half chair, twist boat, through chair. No need. They are just transition states. Okay, you notice that the half chair is the least stable because it's the highest energy due to the repulsive interaction, angle strain, torsional strain, and bond strain. Steric repulsion as well. So just need to know how to draw the chair conformer of cyclohexane. Okay, as mentioned earlier on just now, right, we know that after a ring flip, axial become equatorial, equatorial become axial. So I have illustrated this to you just now, right? The red ball, which could symbolize the Br atom, ring flip becomes equatorial. Now let's investigate a bit. Suppose, right, your Br group is huge, okay, because it's in period number 4. Yes, in period number 4 of the periodic table. Huge electron cloud compared to the size of hydrogen and carbon. So it's actually this big, okay? Don't let this small ball, deceive you. It's this big. So if I put it here, it's great because over here is a lot of space, right? It's not interacting with anything. But if I do a ring flip, oops. Unit lost. If I do a ring flip, take note. So I flip. Okay. It will interact with the 2 axial positions. Alamak, I don't have this axial here, but you notice what I mean is, right, your axial positions from the 3 positions of relative to this carbon here will be interacting, okay, much more than just now, because over here there's just space, but now you see it's interacting. So that's kind of repulsive. We call it 1,3 diaxial interaction. So if you use the Newman projection to draw it out, you see that there's some kind of gauche, right? Gauche strain here. You see it? Remember? Gauche. Sideways. Remember? Gauche. Big ball. Now, under what kind of circumstances can the ring flip be done? Of course, you have to have enough energy to overcome the activation energy, the energy barrier, when you have these transitions. But some other times, it is impossible, like in the case of a third butyl. T-butyl group is what we call in chemistry a locking group. Locking group, okay? That means, right, if you have a chance, okay, if you have a T-butyl group in the cyclohexane, it must be in the equatorial, okay, not axial. Because over here, since this branches out, if I put it here in the axial position, right, it's going to interact very much with the surrounding electron cloud. It's very bad. Very bad. In cyclohexane, for the cis isomers, we know that the both methyl groups are on the same face of the plane. Okay, so here you see is a 1,2 dimethyl cyclohexane, right? 1,2, because they are just adjacent carbons, 1,2. So imagine that these 2 is the 1,2, okay, and they're cis. Cis means pointing the same way. It means up, up, or down, down. So for this guy is up here, right? Axial. What about for this atom? Where's up? This is the up because the other one's down. Okay. So for the first one, this is up and that's down. For the second one, this is up and that's down. So it means that one of the methyl group is going to be axial and the other one going to be equatorial. And if you do a ring flip, then it's similar. Okay, there's no gain in energy because, right, you always have one that's axial, one that's equatorial if it's 1,2 disubstitution, and they're both cis. Now if we have a trans 1,2 dimethyl cyclohexane, trans means on opposite side, across, up and down, right? So see here we have trans, both axial. Very bad because, right, each of them experience 1,3 diaxial interactions. Alright, but if I do a ring flip, okay, again it's up down, so it becomes here. You see that there's no 1,3 diaxial interactions because it's pointing to the equatorial side. So of course, we prefer to undergo a ring flip to adopt the equatorial positions for both substituents. This kind of conformation analysis is very useful for sugars, for the biologists especially, or for the biochemist, to see which one can pack better in the body system. So for glucose, all the substituents on the 6-member ring are equatorial, but for mannose, which we find it in seaweed, Aldehyde, one of the OH group is axial. So you can understand that, right, mannose with double N is more strained than glucose. For polycyclic molecule, at your level you don't have to draw this for me, okay, but for chemistry majors, your friends, they have to. It's challenging, but it's very fun. So let me emphasize the point to you that polycyclic molecules or cycloalkanes are found in steroids that's found in us, hormones. Okay, there are fused rings that are very rigid, totally no ring flip allowed, no matter how much energy you have. So these methyl groups here must stay axial all the time. They have no choice, right? So what's the moral of the story here? Don't take drugs. Okay, don't take drugs. See you.